All right, welcome back to part 3 of the lecture series on sampling. In this video, we're going to talk about this concept called rejection sampling. To understand rejection sampling, let's be really clear on what sampling is. Right? Let's say we have a categorical distribution that looks something like this. And let's say we don't have the data, so we don't know the histogram. Instead, what we have is a distribution. Basically, all we have is an equation. And we would like to generate data out of this equation. And then when we plot the histogram, ideally, we will want 40%, 30%, 30%, right? Because let's say this equation is 0.3x1, 0.3x2, and 0.4x3, right? So in this particular example, then we want 30% to be generated for C, C++, 30% for Java, and 40% for Python. Okay. All right. So how do we generate samples like with the same probability as P of X? Well, there are a couple ways. The first way is similar to inversion sampling. If we generate 100 samples, right, we would like to ideally have 40% of them to essentially have Python, 30%, 30%. So that's one way to do it. Another way to do it is that we can just generate this Python at any probability and any number. So we don't have to generate 100, we just generate as many as we want. But as long as we accept the sample at 40% and reject the sample at 60%, we would essentially still be able to achieve the same histogram, right? So we're still achieving 40% acceptance. So 40% of the time, this will happen. So that's a different concept from ancestral sampling. Ancestral sampling is saying that we're trying to generate the data. So 40% are Python. That's like ancestral sampling. Now we're saying that we can generate the data at any rate. It doesn't have to be 40%. We can generate it at 90%, right? Or 100%, whatever percentages. However, as long as we accept it at 40% and reject it at 60%, then we're still going to get 40%. So these two different ways of sampling has a very, very fine distinction. And you want to listen to what I just said a couple times. And this is a video, so you can go back and listen to it. The first way is you want to generate 40% for Python. The second way is you can generate Python at any percent, any rate. You can generate lots and lots of Python. However, as long as you're accepting it at 40% and then throw away rest of the 60%, you are essentially still generating the 40%. Okay, so you want to get these two ways like sorted out. So the idea of rejection sampling is basically you have a two-step process. The first step is you're trying to generate sample from P of X and you don't know how to do it. Don't know. Instead, what you can do is you can pick another distribution, Q of X, which you do know. So you know how to generate from Q of X. And ideally, what you want is the samples you generate Q of X overlaps with the samples you generate with P of X. So in this case, this right here, you have 3 items. So this is a categorical distribution. So we know this already. So P of X is a categorical distribution. 0.3 x1, 0.3 x2, 0.4 x3. So this is the categorical. And we're going to pretend that we don't know how to sample this. We don't know how to sample this. What we do know is we can sample from a different distribution, which is just another categorical. So it's 1/3 x1, 1/3, x2, 1/3, x3. So they're equal. So this is a uniform distribution. So basically, they're equally likely. Notice how the probabilities are different between P and Q. And I'm saying that we don't have to generate perfectly at 30%, 30%, 40%. We can generate at any percentage as long as we accept or reject at the right proportion, we can still mimic the same result. Okay, so that's the key. So we essentially use Q of X to generate the sample Python. So it's going to generate at 33% instead of 40, 33%, 33.333. So it's going to be generating samples at this percentage. Okay, so that's step one in the two-step process. Okay, so step one is for you to use a Q and generate these samples. Okay, now now that we have Q, what we do, so Q is 33, right? So the red line here, this is where Q is. What we do is we multiply Q by some value K. So we multiply by some value K. And K is a number, a constant value. And that essentially pushes this to another line. Right? So let's say I multiply Q right now is 1/3, and K we're going to multiply by 3. It could be any number, but for simplicity, let's just multiply by 3, which gives us 1, which is right here, right? So if you take your distribution multiplied by K, you get like a line above these P of X. And why do we want to do that? What's the benefit of having this line? Well, let's say, um, let's say now that you have this line, and we generate a sample Python. Okay, so we generate a sample Python, and that was step one of the two-step process. The next step is you need to decide whether you want to accept it or reject it. So let's say over here is between 0 and 1, right? What you can do is okay, 1 second. So over here, probability of Python. Okay, it's right here. This is a probability of Python. What you can do is you can generate a random number between 0 and 1, which is equal to KQX. So you generate a number between 0 and KQX, which is equal to 1, and we're going to call that number U. Well, if this number U falls in this region, right, so it's outside of the region of Python, then we're going to say reject. However, if this number falls into this region, then we can accept. Right, so like think about this a little bit more. If you have 40%, right, and over here is 1, how do you mimic accepting at 40%? Well, you can just generate a number between 0 and 1, and if it falls into the 40%, we accept. That's mimicking accepting at 40%. And then if it falls into this region, which is outside of the 40%, this region, then we reject. And notice how the probability of falling here is 60%. Therefore, by accepting and rejecting using the second number you generate U. So put all these together. Rejection sampling is basically an algorithm where you first pick Q, which is called a proposal. Right? So you pick a Q, and then once you have a Q, you multiply Q of X by some constant. So you have this line. The purpose of having this line is for you to generate a rejection region, right? Obviously, if this line is here, you're never going to reject. You have to have the line above your P of X. And it is when it's above, you create this rejection region. And this rejection region allows you to then generate a second value between 0 to kqx, right? From 0 to kqx. And we're going to call this second value u. If the value u is greater than the probability of x, so if it's greater than this point, then you fall into this region, which is rejection. But if u is less than p of x, then you fall into this point, you accept. And that's essentially the idea of rejection sampling. Now, we use categorical. It's a very easy distribution and it's discrete, but you don't have to stick with discrete. This could be a continuous distribution. So in this example, we're trying to generate the sample. So we start off with this equation, which is a chi-square distribution, and we want to generate these samples. So what we did is we picked q of x to be exponential, which looks like this. But notice if the q of x alone is not high enough, essentially q of x, you will never have rejection regions here. You will never reject. Therefore, what we do is we multiply q of x by some number and push it up. Right? Now that we pushed it up, there's a region of rejection. There's a region of the rejection. So what we do then is once we generate a sample using q, so using this exponential, we'll generate a sample. And then let's say it's this sample. And then what we do is we then generate yet another random number u between 0 and k q x. So let's say we generated 1.5, right? So kq 1.5. So if u is greater than this point, this is the point, probability at 1.5, then notice this is the greater region. Then we reject. Otherwise, we accept if it's less. Okay? So that's the idea. And the reason why it works, if you think about it, is that the probability we will pick u. Did I use u wrong? Let me think for a second. Okay, so let's not do u. Let's say, yeah, I should have used v instead. Anyways, the probability of you picking anything here, right? Let's say this particular value, it's based on the exponential distribution. So it's q u. Let's q of u. Let's say this value is u. So the probability of you picking this point is based on q. And then the probability you will accept u is basically this total height, right? So this is kqu. And then this region, which is pu. Therefore, the probability of you picking u and accepting u is q of u times p of u kqu. And notice how this cancels out, giving you 1 over k p of u. Is this it? Yeah. So notice how you get this back, probability of u. And this is the reason why rejection sampling works. And some might say, well, you're not generating p of u. You are generating p of u divided by k. And that's true. But if you think about it, like if you generate, let's say you generate 100 samples, right? No, 100 samples. And we have a Bernoulli distribution of 20% and 80%. So what's your histogram going to look like? Well, 20, 80, right? 20, 80. Well, if your probability is less, let's say it's 1/2. So k 1 over k times p of x. And let's say k is 2. So 1 over 2 p of x. If that's the case, then what you'll end up having is instead of 20/80, you end up having 10/40. So you're going to get this distribution. Right? Well, the histogram may have different numbers, but the proportion is exactly the same, right? So it doesn't really matter. So that's the reason why 1 over k doesn't really matter. Okay, so here, sampling is how a lot of the generative model works. And here I want to go over the very basic algorithm of how sampling works. Let's say you have some data set, and we have a function that maps the data set to a point in a Gaussian distribution. So we have we have this data set, and this could be like many dimensions, and this could be images, video, text, whatever. So this is the data set, and we have a function that when you plug the data set into the function, a single sample from the data set into the function, it will map it to a point in Gaussian distribution. So it will say it's this point, for example. And then from this point, we have an inverse function, f inverse, that maps it to the original. So ideally, xi and x hat are very close to each other. They're approximately the same, ideally the same. So this is the point. Like um, in this generative model, you have a data that and a function that maps it to a Gaussian and then maps it back. And how do we go about learning these functions? Well, we can learn this function using this objective. We have a mean square error saying that we want the input and the output to be the same, right? We're trying to minimize the error between input and output. And then we have this measure of KL divergence. So we will learn KL divergence next class, but the idea is KL, if you have a probability distribution P, and then you're trying to mimic the probability distribution using Q, how do you measure the error between them? So you're trying to use Q, create a Q that's as close to P as possible. And the way you can measure error is through KL divergence. So KL divergence essentially measures the difference between two probability distributions. Remember, in mean square error, we had our prediction, and we had the truth, right? And the goal is that we want to minimize the difference between the prediction and the truth. Here, instead of predicting a number, we're trying to make sure we're trying to predict a distribution, an entire probability distribution. And we're trying to minimize the error of the distribution that we have and the desirable distribution. And what we're saying here is essentially when we map the data through F, we want to make sure that the result is a nice Gaussian distribution. We want f of xi, the probability of this, to be as similar to the Gaussian as possible. So this objective essentially ensures that we have a function that maps the input output to be same, and in the intermediate step, this step is a Gaussian distribution. Now, okay, let's say this works. Why is this useful? This is useful because this allows us to generate samples. Now, let's say we have your data, and your data are pictures of people's faces, right? Picture of faces. So these are all pictures of faces. Well, if you have the picture of the faces, now you take one single sample, you map it into a Gaussian distribution, and then you map it back. So this one, you're going to get it back, right? You're going to get it back. Okay, so this implies that all the possible samples could be mapped to a point in a Gaussian and can be mapped back. What happens if you just forget about this part and just generate a random Gaussian point, right? You just randomly generate a point right here, x hat. And then we plug x hat into the inverse function. What do you think this thing would be? What is the result of this? Well, the result of this would be image of a person's face, right? So essentially we can generate samples from a Gaussian, and through this mapping generate random samples that you may or may not have ever seen before. So this could be a face that you have never seen, that doesn't exist, right? And this is for like image of faces, but you can imagine you can generate image of anything. Like here are examples. You can generate image of anime, right? Female, blonde female, cat, porcupine. And once you understand that this is really just learning, what this is learning is it's ultimately learning the P of X for the data, right? Once you know the P of X, what's happening is it's generating a sample. And P of X could be anything. P of X could be pictures, videos, audio, music, right? And therefore, whenever you generate a sample, you will get a sample of music, audio, music, pictures, right? And what is interesting is once you understand this condition, this probability, you can add conditions. Like you want to generate image given that it's pictures of a cat, right? So here it is. Here's a cat. Or you can condition it based on it being a dog. And what this algorithm I just shared with you guys is the basic idea of how stable diffusion and variational inference works. There's obviously more detail of how to actually get it to work, but the general idea and the gist is basically like this. Yeah? So over here are examples of pictures. I also use AI to generate bunch of songs, right? Bunch of songs. So when you have the chance, feel free to check it out. Some of these songs I included in our video series, so you can listen to them, and they're not bad. Like they are quite catchy. All right, so now that we're done with rejection sampling, the next sampling method is called importance sampling. Okay, so in importance sampling, you are actually not taking a distribution and generating samples. You're doing something else. Right? You're trying to solve integrals. So I'll show you an example. Let's say we had this integral we're trying to solve, and we learned previously that if you want to solve this integral, you can either do it by hand or you can approximate the result to be 1 over n summation of fxi. So you can get rid of this and just plug the samples you have from P of X into Xi, average it together, and the problem is solved. Okay, so that's what we learned previously. Now the problem is, what if you don't have samples? What if you don't have samples for this? Well, then you have to generate your own samples. But this could be very difficult to generate. Well, if this is difficult, then what we could do is use importance sampling. Right? Importance sampling is very useful. What we do is, if we don't know how to generate sample from P, we just pick another distribution, Q, that we do know. So we know how to generate samples from Q. Okay? Well, if you know how to generate sample from Q, we can multiply this by Q divided by Q, which this is equivalent to multiply by 1, which is okay. You can multiply things by 1. This means that we can bundle this whole thing together and call it a different function. We're going to call it G. This implies that if we generate samples from Q, which we know how to, with the samples here, we simply plug it into G of xi. And when you plug it in, you average it together, it's mathematically equivalent to solving the original integral. So if you have complicated integral and a distribution you don't know how to like sample from, then important sampling is an example of how you can do this. All right. Oh, there's another sampling. I'm gonna leave KDE sampling to a separate video, so you can go over the KDE in that other video. All right. So, in summary, sampling allows you to generate samples from a distribution, and these distribution could be samples of faces, speeches, novels, art, or music. And whenever you generate a sample, you get a sample of a face, a sample of an artwork, or sample of a music song, right? And it also allows us to solve very difficult integrals. And then we're going to talk a little bit more about this, right? And this with this concept called Monte Carlo integration. By understanding sampling, you can use it to solve not just any function with a p of x. You actually don't even need the distribution. You can just solve the integral of any function, and I'll show you how this works, right? Um, so here's an example. We're trying to solve the integral between 0 and 2. So what we wanted to do is ideally we want to generate samples. Like we don't have a p of x, right? But we want to generate samples between 0 and 2, right? Well, one of the simplest distribution you can have is a uniform distribution, uniform between 0 and 2, right? So therefore the height, it will be p of x equals to 1/2. The reason why it's 1/2 is because the area has to equal to 1. It's a probability distribution. So 2 times 1/2 is equal to 1. So we don't have this distribution, but what we could do is add it in. Right? So let's say we're trying to solve this f of x, and the f of x is some function that looks like this. So we don't have a p of x here. But what we could do is just add this uniform distribution. We just add it in. Well, how can you do that? Well, you can do that as long as you get rid of it somewhere else. So 2 divided by 2 is equal to 1, right? The same trick that we just saw. Therefore, now, given there's a 2 here, we have a uniform distribution that is generated between 0 and 2. This implies that if we just generate samples from this uniform distribution, we just generate the samples there, then we can so this is p of x here, right? So if we can get rid of the p of x and simply generate samples from this uniform distribution and plug it in here. And then when we take the average times 2, right? 2 is still there. Then this is mathematically equivalent to solving the original integral. Okay, so this integration is really cool that you can essentially add your own distributions because uniform distribution is a constant, right? And you're trying to integrate between 0 and 2, so you pick 0 and 2. So you're generating samples within within the interval of interest. And then you can use those samples to solve a complicated integral. All right. So that's the general idea of Monte Carlo integration. All right. So for your next exercise, I want you to write the code to solve the following integral. Now it's from 2 to 3. Okay. So the distribution p of x you want to add is this one. So that's the integral. Okay. Now, once you're done with that, you want to solve the second one. You want to write another sampling that solves this integral. You want to identify p of x, which here p of x is an exponential distribution. So that's the p of x, and you can pull that out and generate samples based on that. Okay, I think that's it for today, right? Oh, there's one more. Yeah, we want to solve the following two. Yeah, this is the very last one. See if you can solve this one as well. Okay, I think that's it for today. I will see you guys in the next lecture.